Right, hi guys. Welcome to another lesson. We might have to, so I'm planning to reduce this to one lesson a week, but because of the plans that are coming into place, which I'm sure you'll hear about in more detail soon, but because of the plans that are coming into place with you being able to go back into school for some time, not full time, but being able to go into school a little bit, um, we're probably going to move these to Fridays just so that I'm sure that everyone can access it because as far as I know, you won't be going in, nobody will be going in on a Friday. So that's just a little bit of some thoughts in terms of when we will be doing these. As far as I know at the moment, we won't be having any in-school computer science lessons. They want to focus more on the core subjects, which I can understand. So it's just an idea of what's going on in terms of all of that. So today's lesson, we're going to be looking at the bubble and the merge sort. Now, I have previously gone through bubble sort with you in one of your lessons before. I had intended to move on to the merge sort as well, but I think it was at the end of a unit and we were kind of rushing. So I'm going to just go back through it. It might take a couple of lessons to go through this, but we'll hopefully be able to get as much as we can out of this. So looking at the bubble and the merge sort algorithms. So we've previously talked about the searching algorithms of linear search and binary search, where linear search is just one item after another, a bit like our searching through a for loop, for example, whereas a binary search is splitting your data into two each time, and as long as it's in order at the beginning. So that's a quick reminder of the linear and the binary search. If you have forgotten about that, then please have a look back through that video where we talked about that. I might just have a quick look back through that to make sure I covered everything in enough detail. But anyway, so looking back at the idea of what is a bubble sort. So it is a very simple method used to make sure a data set is put into the right order. Very, very simple. It's not very complicated at all. So that's the good part about it. One of the bad things, so you've got your array of data or your list of data, which is looked through continually. So traversed means going through it. And adjacent pairs of elements are swapped if they're required until the array is placed in the desired order. So I'm going to show you an example of how this works in a moment. A bubble sort will be likely to require multiple passes through the array. This means it's quite an inefficient algorithm because you need to keep going through the same stuff over and over again. Okay. So we've talked a bit about efficiency of algorithms. This is quite an inefficient algorithm, but as we've mentioned before, algorithms that are more efficient might be a bit more difficult to get your head around. So whereas algorithms that are inefficient are really simple to understand. So I'm just going to go through. Step one is to compare the first two numbers. If your smaller number is on the right, you swap them and then you write out the remainder of your list. Step two is to move to the next number in the list. Compare those two numbers. If the smaller number is on the right, swap those two numbers. Write the remainder of your list. You repeat step two until the last two numbers have been compared, and that completes the first pass. When we say pass, that's going through one set of the data and going through the entire list once. Your second pass in step 4 is repeating steps 1, 2, and 3, and you don't need to compare the last two places because you know that the last item should be in the right place because it was bubbled up, and I will show you how that works in just a moment. Then step 5 is to, for the third pass, repeat steps 1, 2, and 3, and there's no need to compare the last 3 places this time. So the last 3 places you don't have to compare because you know that the last 2 are correct. So I'm going to show you this website. I'm going to send a link to it because I think it's actually really useful for you to access. When you access this website, it will come up with this box here. Let me just paste it into the chat. So there it is. You can just click that escape button at the bottom. And you can see we've got a list here of unsorted data, so 3, 44, 38. And just to give you a visual representation of the data, we've got like a bar chart with the different data involved. So if I click on sort and then go here, what I can do, let me just slow this down for a moment and just go back to the beginning. What you'll see here is some information here, and it says do. I might zoom in a little bit so you can see what I'm talking about. Do, and then swapped equals false, and for I equals 1 to index of last unsorted element minus 1. If the left element is more than the right element, we're going to swap the left element and the right element. And we're going to say that swapped is true. And we're going to keep doing this while swapped is true. Okay. Now, this is a piece of pseudocode. Obviously, if you were to write this directly into something like Python, it wouldn't quite work because there's a few extra bits that you'd need to include. You need to write the method called swap. You'd need to make sure you kept track of what the index of the last unsorted element was as well. So what I'm going to do, I'm going to run through this bit by bit. So just going to go, so the swapped flag has been set as false at the beginning, okay? Then it's going to go from I is 1, which is the first item in our list, to, there are 14 items in this list, so it's going to go up to 1 to 14, okay? Then the next thing it's going to do, it's going to compare these two elements, 3 and 44. It's going to go, is the left element more than the right element? In this case, no, it's not. So we're going to move on. Is the left element more than the right element? Is it? Yes, it is. So what we're going to do is we're going to swap. And we're going to set swapped to true. Okay? Same thing again. Is the left element more than the right element? Yes, it is. So we're going to swap. And we're going to move up. Even though this element is smaller, we're going to keep going up. Is 44 more than 47? No, it's not. So we're going to move on. Is 47 more than 15? Yes. So we will swap them. Is 47 more than 36? Yes. So we're going to swap. I'm just going to let it run through. It's going to run a little bit faster. And you can see it's comparing these values. 47 is more than 27. 47 is more than 2. 47 is more than 46. 47 is more than 4. And you can see it sort of bubbling up to the top. And then, is 47 more than 50? No, it's not, but 50 is more than 48. And at this point, you can see this has turned a different color because it is the last unsorted element. Okay? The index of the last unsorted element. So the index of that is 14. So it's now going to be 13. So if I move on to the next part, so the index of the last unsorted element is 13, 14, and then minus 1 makes it 13. And we've set swapped to false, okay? Is 3 less than 38? Yes. So we're just going to keep going, keep doing that. Let me make it a little bit faster again. You can see it kind of bubbling up. That's why they call it the bubble sort. Can you see this bigger number is like bubbling up to the top? Okay. And we're going to keep doing that through each time. So you can see that the last 3 don't need to be swapped because they are they're being they're already in the right order. Okay, and we can carry on. Just gonna pause it in a couple of moments because, so at this point, 2, 3, 4, 5, 15, 19, 26, we can see that this is in order. So what it's doing is comparing all of these values, and at the beginning we set this swapped to be false because now once we get to this point we can go, okay, swapped is false, so I don't need to do the loop again. So if a lot of your data is already in order, you don't need to worry. Your bubble sort is actually going to be quite quick. If you've only got one item out of order, for example, it will go to the right place and then that would be it, done really quickly. Okay, so that's basically the bubble sort. So one of the things, so you stop when a complete pass produces no swaps. So here's another example. So you've got your first pass, you're comparing 7 and 2, you're swapping them round because 7 is more than 2. Comparing 7 and 9, they stay the same because they're in the right place. Comparing 9 and 5, they swap. Comparing 9 and 4, they swap. And then you can see that 9 is in the right place. So this is, how many comparisons have we made? Well, we've made 1, 2, 3, 4 comparisons. How many swaps have we made? We've made 3 swaps. Okay. So second time round, we start with this same number, but we're comparing these two numbers this time, 2 and 7. We can keep them the same. 7 and 5, they can be swapped. And then 7 and 4, they can be swapped. So now we've got 7 and 9 at the end. How many comparisons did we make? We made 3 comparisons. You can see the numbers in different colors to show the comparisons. And then we made 2 swaps here. Okay. Our third time round, we're comparing 2 and 5. They can stay the same. 5 and 4 can swap. And then you can see that that 5 is now in the right place. Okay. How many comparisons? How many swaps? 2 comparisons, 1 swap. Okay. And then, even though we can see that this is in the right order, we still need to check. The computer doesn't know whether these two numbers are in the right order, so it needs to check. So it compares 2 and 4, goes, okay, they're in the right order, so it only needs to do 1 comparison and no swaps. Okay. So you can see it takes a bit of time to get through this. There are 10 total comparisons and 6 total swaps. Okay. So what I would like you to do is to use a bubble sort to rearrange these numbers into ascending order. So 13, 16, 10, 11, etc. Oh, let me go back. And state the number of comparisons and the number of swaps for each of the first 3 passes. So a reminder of what a pass is. So all I need to see is that the values at the end rather than each individual swap. You might want to explain how that works. You might want to write it all down to kind of show how it works, but this should help. This should you don't need to show every step. 2a uses bubble sort to rearrange the following numbers into ascending order, showing the list of numbers after each pass. So 6, 2, 3, 5, and 4. Okay, and then write down the number of comparisons on the first pass. So I only want to see each pass. I don't need to see the whole thing, but if you feel like you need to write out the whole thing, then that you can do that too. So I would suggest opening like a Word document, or if you think you'll be able to open like a Paint or something like that to be able to go through and have a go at these. I'm going to give you how long am I going to give you? 5 minutes at first, and then let me know where you're up to, and we'll see from there. Okay, guys, so I've given you a bit longer than 5 minutes because I was trying to do it alongside with you, but just to kind of go through some of this with us. So rearranging these numbers into descending order, obviously we can just go, oh, well, 4 is the least, 6 it goes above that, 7 goes above that, and then 10, then 11, and 12, and 13, and 16. Easy, right? Computers don't work like that, although what you're kind of doing there is using what they call the insertion sort, where you're kind of looking at a number and going, okay, that one this is the number, trying to find what I can recognize as the lowest number straight away and putting that right at the beginning, then going, okay, what's the next lowest number, and so on. You're almost doing like a backwards bubble sort there, really, but you're not having to compare each and every item every time. So what I've done is I've actually put this into the Visual Go thing here, and what we should be able to notice is the items bubbling up as they have before. So I'm going to run this. I don't know why it's not. Sort Go. I didn't click on that, so it's just going through, comparing items. In fact, what we should really be doing is checking how many comparisons we've made. So let's just go back. We can look at, we go 1 comparison, 2, 3 comparisons, 4 comparisons, 5 comparisons, 6 comparisons, 7 comparisons. Now, oops, go back a moment. Now, if you look at this, there are 1, 2, 3, 4, 5, 6, 7, 8 items in the list. Now, generally, we are going to be making the same amount of comparisons that there are in the list -1, the items in the list -1. So in this example, there were 1, 2, 3, 4, 5 items in the list, and there were 4 comparisons. And then because effectively your list is getting shorter, your amount of comparisons can go down until you get to the passes where you're, if everything was already in the right order. Okay. And so the number of swaps for the first 3 passes, we can also work that out if we go back to the beginning. So drag this all the way back, and we can just run through it really quickly. Not swapped, 1, 2, 3, 4, 5, 6 swaps. Okay, and then 1, 2, 3, 4, 5, 6 swaps again. And 2, 3 swaps. You can see that the third time round, the swaps got reduced because more of the numbers were in the correct order already. Okay, so that's for that one. I'm just going to set up for the other one. So these are 6, 2, 3, 5, and 4. Okay. And oops, let's just start at the beginning. So what I would expect you to do is every single time this changes, as in the numbers change order, you would write down the numbers. Okay, so you write first thing you'd write down is obviously 6, 2, 3, 5, 4. The next thing you would write down is 2, 6, 3, 5, 4. Then you would write down 3, 6, 5, 4, etc., etc. And you'd even 5, 6, 2, 3, 5, 6, 4, and 6, 2, 3, 5, 4, 6. And actually, even if you're comparing two numbers and they don't have and they're not swapping, you'd probably still write them down again because you've compared, but you haven't swapped. Okay, so 2, 3, 5, 4, 6. This here would be it after the first pass. You can see that this item here is already sorted. It's the highest number in the list. And we're going to keep going through. And it just checks now, oh, well, I don't need to swap anymore, so we're okay. All right. So hopefully that should have given you a vague idea of how to work through bubble sorts. So after the first pass, one number will definitely be in the correct position. In the chat, quickly tell me which number is that, in which position would that be? And then I'm going to come up with the other questions without showing you the answer for this one. And, oops, sorry. Also, after each pass through the data, are there more or less comparisons made each time? So quickly in the chat. Just going to see if I can add these in. Okay, so let's just check my animations on this. Okay, sorry, just playing around with animations here. So, I'm not sure why it's come up with that, but so after the first pass, one number will definitely be in the correct position. The last number will be in the right place after the first pass, and it's one less comparison per pass. Yes, each pass through the data requires one less comparison than the pass before, or that should say than instead of that. Another couple of questions. Eventually, the algorithm stops. How does it know when to stop? and write down a list of 5 numbers which will need just one pass through the list and no swaps. So when does it know to stop, and what 5? Give me an example of some 5 numbers that will not need any swaps and the order in which they are. Good. So it stops, when there are no more swaps. So when there are no swaps in that pass, correct, the algorithm will stop. We've got other people watching, so I'm sure there are more people who can give an answer. For the last bit, what 5 numbers? I mean, it could be, you could come up with a completely different list of numbers than someone else and still be correct here. Yeah, so 1, 2, pi, 4, and 5. Yeah, I'm assuming that's pi, just from a quick look at it. Yeah, so 1, 2, 3, 4, 5. As long as the numbers are in order, it will look through the list and will go through, and it won't need to swap anything. So it only needs one pass through the list. So we've just looked at a set of 5 numbers that will need the maximum amount. So we've just looked at the minimum amount of comparisons needed. What about the maximum number of comparisons and swaps, and how many comparisons would be needed in total? Also, what's the maximum number of comparisons for a list of 10 numbers? So a list of 5 numbers that will need the maximum number of comparisons. If you think about the fact that a list of 5 numbers that have the minimum amount of comparisons, that they are in order, what would the maximum number need to be? And for comparisons for a list of 10 numbers, how many, what's the maximum number of comparisons you would need for a list of 10? You might need to do a little bit of maths here. So 5, 4, 3, 2, 1 is a good example, and I think that's exactly the example I've got here. Something that's in the opposite order than it should be would be something that would use the maximum number of comparisons, because you have to bubble up the 5 like this after the first pass, then you have to bubble up the 4, then you have to bubble up the 3, then you have to bubble up the 2, and until you get to checking this final pass here. Okay. So there are 4 comparisons, 4 swaps, 3 comparisons, 3 swaps, 2 comparisons, 2 swaps, 1 comparison, 1 swap. So you can see straight away that anything that has 4 comparisons, so anything that has 5 items in it, if it's in the opposite order than it needs to be, it would actually be 10 comparisons, 10 swaps and comparisons in total, because you've got 5 items. You still need to compare 1 and 2 to make sure they are in the right order. So don't forget about that last one there. And then what's the maximum number of comparisons for a list of 10 numbers? It doesn't quite double. Obviously, you've got, so it goes, it'll be 9, then 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1. Okay, so if you add all those numbers up, we do 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 gives us 45, correct, Jordan. So 45 is our list of 10 numbers, okay? Because you'll start at one less than, you'll have one less comparison than the amount of numbers there are, okay? So hopefully you've kind of got the gist of how bubble sort works. We might not be able to go through all of merge sort, but I would like to give you a brief introduction to the idea. So bubble sort is a very simple, but it's a very inefficient algorithm. Now we're going to look at a related algorithm, but it's a more sophisticated one. This is the merge sort, okay? A merge sort is a method of arranging data by splitting a list into elements and merging those elements together until an ordered list is obtained. So these are what we call a divide and conquer algorithm. The binary search is another divide and conquer algorithm where you are dividing the effort in a way. So you're dividing the problem into a small number of pieces and conquering by solving each piece by repeatedly applying this dividing, by repeatedly dividing each part. So you don't have to look at the whole thing at once. You can look at parts at a time. And then you combine those pieces together into a solution. So how does merge sort actually work? So what we're going to do, we're going to stick to some examples where an even number of elements are sorted, just to make this a little bit more obvious of what's going on. So what we do is we repeatedly split the array or the list in half until there are only individual elements left. So we've got our array here, 5, 8, 4, 2, 19, 34, 56, and 7. This needs to be sorted. So we're going to split it in half. So we've now got 2 separate arrays or lists. And then we're going to do the same thing again. We're going to now have 4 separate lists or arrays. And then into individual elements. Okay. Then what we're going to do, we're going to compare those values that we just had. So we've got 5, 8, 4, 2, 5, 8, 4, and 2. Oh, that's not correct. That should have been 19, 34, 56, and 7. That's just my bad in terms of copying over values. But we've got our different 5, 8, 4, 2, 19, 34, 56, 7. These are individual lists now. Okay. Now you can see, you can imagine that a computer goes, okay, you've got to keep track of 1, 2, 3, 4, 5, 6, 7, 8 different lists now, which is a bit complicated and a bit more intensive on the computer, but it actually runs much more quickly because once you've added lists together, it just goes more. You can get your values sorted much more quickly. So what happens is it compares these two values and goes, okay, whichever value is the smallest will go first in the list, and then it will do the same again with this one. So it will go 5 goes first, and then 8, and then it will do the same here. Which value is the smallest? 2 goes first, and then 4. Okay, what value is the smallest here? 19, and then 34. What value is the smallest here? 7 is the smallest, and then 56 comes after it. So it'll look like this. Okay, so we've got 4 lists this time. Okay, and these lists are in order. Okay, so now we're going to compare these lists with each other. 5 is going to be compared with 2 because we know that 5 is the smallest item in this list and 2 is the smallest item in this list. So it's going to compare 5 and 2, and it's going to look at 2 and go, okay, well 2 is the smallest, so we'll put that in first. So then we go, okay, we're not going to move from this value because we know that that wasn't the smallest, so we're going to keep looking at the 5. And we've already looked at the 2, so we're going to now look at the 4. And we're going to compare 5 and 4 and go, okay, 4 is smaller than 5, so we're going to put 4 in. And then we now know, because this list is empty, that this list, the entirety of this list, which we know is already in order, can just be put at the end. Same idea here. 19 is compared with 7. 7 goes at the beginning. 19 is compared with 56. 19 goes at the beginning. and then 34 is compared with 56. Sorry, 19 goes after 7. 34 is compared with 56, which then goes next in the list, and 56 goes at the end. Okay, so now we have two lists that are in order. Okay, and same idea again. 2 gets compared with 7. 2 is the smallest. 4 gets compared with 4 gets compared with 7. 4 is the smallest. 5 gets compared with 7. 5 is the smallest. 8 gets compared with 7. This time 7 is the smallest. Then 8 gets compared with 19 and goes, okay, 8 is the smallest. Now because this array or this list is empty, the rest of this array can just be added in because we know that this entire array here is in order. Okay, so now we have a sorted list. You can see that we don't have to do quite so many comparisons. Okay, so what I'm going to do is I'm going to show you this exact same idea that we've just run through. Let me just get it up so that I can have it ready to go. So this is, oh, I've lost the, let me get this back up. So I'm going to add in a list, create a list, and I'm going to just, I didn't copy that correctly, obviously. Let me just, no, okay, I'll just have to type it in myself then. So it was values 5, then 8, then 4, then 2, then 19, then 34, then 56, then 7. Okay, so I'm going to show you what this looks like in bubble sort first. Okay, it doesn't like the number 56, so I'm just going to change that to 50 because it's almost the same. Okay, so we've got our numbers, and I'm going to show you what it looks like in bubble sort, and then I'm going to show you the difference in merge sort. So I'm going to run that. So this is a bubble sort again. Okay, so you saw it took a fair bit of time. Now, if I shouldn't have gotten rid of that. 5, 8, 4, 2, 19, 34, we said 50, and 7. Okay, so if I press go, and then sort, go, just what I'm going to quickly do is run through this bit by bit like we just did. So what it's doing is it's splitting each element into positions of size 1. So we are in, oops, I didn't realize we were running. So it's, let me just go back one more. Okay, so you can see we've got different colored blocks. These are all different arrays at this point. So what it's going to do, it's going to compare these two arrays, okay? And it's going to go, okay, 5's the smallest, and then 8. And then it's going to put both of those items back. Then it's going to compare these two, 4 and 2. And it's going to go, 2 is the smallest, and then it's 4, and I'll put those two back. And you can see this is one array now, or one list, and this is another array, or one list, okay? Then it's going to compare 5 and 2. So this side hasn't been sorted yet, but we're going to sort one side at a time from the looks of it. There are multiple ways we could do this, but this is the way that this algorithm is deciding to do it. Very similar to how you could do it in a different, like you could sort this in entire half as well first. So it compares 5 and 2, 2 is smaller, 5 and 4, 4 is smaller, then 5, then 8. And it puts them all back. So now we've got one array here. Now we're comparing 19 and 34. 19 is smaller, so those can go back. Comparing 50 and 7, if I move these out of the way, you'll see 50 is bigger than 7, so it comes last. Then it's comparing 19 and 7, 7 is smaller, 19 and 50, 19 is smaller, 34 and 50, 34 is smaller, and then 50 at the end there, everything goes back. Comparing 2 and 7, 2 and 7, 2 is smaller, 4 and 7, 4 is smaller, 5 and 7, 5 is smaller, 7 and 8, 8 and 7, 7 is smaller, 8 is smaller, and then we've not got anything to compare it to, so we can just put the rest of them into that array. Okay, I'm just going to run this really quickly. Oh, no, sorry, let's put it back onto fast. Okay, so I'm just going to make sure I've got these values and go back into bubble sort with the same values. And you can see already that it's just taking that little bit longer, or it feels like it's taking that little bit longer. Depending on the list of data that you've got, sometimes the bubble sort will seem quicker than the merge sort. But if, for example, I ran this piece of data, don't know why it's right at the end. If I run it, sort, that might help. You can see that this is a much more efficient way of doing it because there's a lot of data to deal with here. Okay. And in this example, there's an odd number of items, and actually it doesn't really matter if you've got a list that's 1 long when the rest of them are 2 long. Okay, so hopefully you kind of have a vague idea of how merge sorts work. So our example was a simple one. That array contained just 8 elements and it's easy to split them to pairs. The full algorithm has to cope with the possibility of odd numbers of array elements, of much larger arrays, and numbers which don't easily split into pairs. As with those searching algorithms, a more complex process requires fewer steps to complete than the simpler, but more basic alternatives. So the binary search that we talked about before involves bisecting or putting a data set into half until a match is made, and a similar process occurs here in the merge sort, where you are splitting in half each time until you are certain it's working. So here we're talking about the recursive operation of the underlying algorithm. So it repeats itself where required. Recursive isn't quite about repetition, because that's iteration, but recursion is more about looking inside something to be able to do something else. So I'll go into more detail about what recursion is another time, but I think that's kind of an A-level topic more than a GCSE level topic. So if you want to find out about recursion, maybe do a bit of a Google search, because it's quite interesting actually. So as you can see from here, these both started at exactly the same point, and depending on which things you have, they will sort in different values. So bubble sort, when it's nearly sorted, is actually going to be quicker than merge sort. But in pretty much every other circumstance, merge is going to be quicker. Okay, so we've talked about bubble sort, we talked about merge sort. What comparisons can we make of those two techniques? So I did manage to get through both techniques, both bubble and merge. Hopefully you've been able to kind of understand fairly well how they work, how that in bubble sort you've got it kind of bubbling up to the top, as you can kind of see here. these are bubbling to the bottom, well, the smallest values on the top, etc. But the same process, the same principle applies here. You can see that for bubble sort, if it's reversed, that's the worst case scenario. Whereas in merge sort, it's actually fairly straightforward to sort it out if it's been reversed. Okay, though that is still probably the worst case scenario. So, and in A level, you start talking about things like big O notation to talk about how efficient your algorithms can be and what would be the best case scenario and what would be the worst case scenario. As you can kind of see here, different kinds of sorts will have different, it will be better in some circumstances, but worse in other circumstances. And you can do searches for different sorts on YouTube. There are some really fun YouTube videos of some of the different sorts being shown, and they've got some fun little, it's quite pretty to watch. So if you're one of those kind of people who likes looking up data being sorted a bit like this, but in a bit more, it is very interesting to look at. So maybe look up bubble sort and you'll find some. Let me quickly just see if there we go. So I'm not going to play it because obviously YouTube's algorithms and whatnot, but you've got this video here is quite an interesting one. You've also got ones which show you lots of different visualizations. You've got ones that show you in different colors, which I think are a lot prettier to look at, but it's just very interesting to watch. And if you can get your head around this bubble sort and the merge sort, in your exam, merge sort is usually mentioned, and for example, you've got to try and show how, maybe talk about the differences between bubble sort and merge sort in your exam, and being able to take some data like this and merge it and kind of, so you might be given this top row and you'd be asked to fill in the rest of the rows, for example, in an exam. Okay, and obviously if you fill in your rows correctly, then it will come up, it should count. Obviously you'll come up with the final answer in the correct order, but these parts are the bits you'll be marked on to see what order you managed to do them in. You might also be asked to do your bubble sort, where it shows you, let's go move back a bit, where this kind of thing, where it's asking you to sort some numbers using bubble sort and show each line as it goes through. So showing something like this in your exam would be the best way about that, to make sure there's no ambiguity, so that they know exactly what you're talking about. Okay. Right, I think that'll do it for today's lesson. I will see you at some point next week. I'm not sure whether I'm going to make it Wednesday or Friday. I will make up my mind before then, obviously, but I hope you all have a lovely week, and I hope you've been able to kind of understand how bubble sorts work and how merge sorts work. As I say, do a bit of research into bubble sort and merge sort. Maybe have a look at that website that I posted into the chat again, and play around with the different kinds of sorts. There are, as it says at the top here, bubble and merge. They're the two that are mentioned in the bubble and merge at the top here. These are the two that are mentioned in the AQA specifications, so they're the ones that will come up in an exam. But if you're bored, you can have a look at the different kinds of sorts that exist as well, because they're a bit more interesting. They can be quite interesting to watch, to see how those work. Okay, so I will see you at some point next week. Have a good week. Bye, guys.